So the first thing tonight is you have some homework for me. I need a name and a section number. Johnson City, you're 521. You folks here in Kingsport are 531. You folks that are streaming, you're 990. You're emailing it to me. Remember that. You emailed it to me, didn't you?
Yeah, I thought it was good.
No, that's cool. We'll talk about that. Now, homework number 2 for Tuesday. I believe that's the 15th. I picked quite a few problems this time. 2.7, 2.9. Now, those two are in the middle of your chapter. Those aren't at the end like, I think all the ones I picked last time. There's 2.18, 2.19, and 2.22. 2.23, 2.24. Now look, these are all multiple choice ones. There was 5 of them I picked this time. And then I picked 2.31 and 2.46. Now, 2.7 is going to require a histogram. 2.31, 2.7 is going to require a box plot. Sorry. 2.31 is going to require a histogram. And this 2.46 is going to require side-by-side box plots. Now, if you want another thought about 2.46, you should go back to Tuesday where I did problem 2.47. Remember where we had the 3 groups, the good weather, the bad weather, and the no weather, and we were looking at the tipping? Here, instead of weather, they're looking at smells in the restaurant. It's like a lemon odor, a lavender odor, and no odor. Do people actually spend more? Now, a couple thoughts about this. In 2.7, and I'm going to point you to the page here. 2.7 is on page 55, and it says fuel economy for mid-sized cars. The Department of Energy provides fuel economy ratings for all cars and light trucks sold in the United States. Here are the estimated miles per gallon for city driving for the 205 cars classified as mid-size in 2014, arranged in increasing order. Okay, the file that goes with this out of Minitab is mid-cars. It says, give the 5-number summary of this distribution. Now, they're in order. So you don't have to put them in order, right? You're just going to take 206, add 1, divide by 2 to find the median, look at the first half, second half to find the quartiles, yeah? So, you should be able to do that one by hand. They're in order for you already. It says, draw a box plot to show the data. You're going to use Minitab. There's not more than one group. You're just going to have a single box plot here, right? What's the shape of the distribution shown by the box plot? Is the median in the middle? Is the median closer to the first or the third? Which features of the box plot let you know this conclusion? Are there any observations unusually large, unusually small or large? Is anybody stuck out on the box plot? Right? Remember, Minitab kind of gives you a hint you see anybody that's extreme, right? The little stars, the little asterisks. And then in 2.9, yeah, I know. I didn't have a graph for that or anything. I just want to point something out to you. It says, exercise 2.7, which is the other one you're going to do, gives the estimated miles per gallon for city driving for the 205 cars classified as midsize in 2014. In that exercise, we know that several of the MPG miles per gallon values were unusually large. I'm assuming you're going to see that in your box plot, that there's some stuck out there with little asterisks, right? It says, which of these are suspected outliers by the 1.5 IQR rule? Remember you set the upper fence? You only have to set the upper fence here. It's asking you unusually large. Remember, you're going to take the third quartile plus 1.5 times IQR and set that fence. If you got a miles per gallon bigger than that, you're a suspected outlier here. You're a possible outlier. We talked about that formula on Tuesday. Okay, and then what was my other ones here? Oh, 218 through 219, 222, 223, 224, hell, they're all multiple choice. All right? 231, guinea pig survival times. Here are the survival times in days of 72 guinea pigs after they were injected with infectious bacteria in a medical experiment. Oh, that's kind of bad. No, I just looked to see what the questions was. I didn't actually see the setup. But we're going to look at survival of guinea pigs. Survival times, whether of machines under stress or cancer patients after treatment, usually have distributions that are skewed to the right. Okay, they're telling us that, right? They give me the data, right? So there's 72 guinea pigs, and it's their survival time after they were injected with whatever this was. Is the data in order? Yeah, it goes from smallest to largest, right? It's in order for you again. It says, graph the distribution and describe its main features. Histogram. Right? Describe its main features. What's its shape? Don't get too carried away about giving me the center and spread. You're going to calculate those. It says, does it show the expected right skew? I don't know. You'll have to look at the histogram and see. Do I see it skewed to the right like we are expecting it to have? Which numerical summary would you choose for these data? Do you want the mean and standard deviation, or do you want the 5-number summary? Folks, if it's skewed to the right, which hand do you want? Remember, the 5-number summary works best for you see skewness and or outliers. The mean and standard deviation works best when they are roughly symmetric and no outliers. If this thing actually shows the right skewness, you want to calculate the 5-number summary. The data is in order. You should be able to do that relatively simply right there. Calculate your chosen summary. How does it reflect the skewness of the distribution? If it is right skewed, what are you expecting to happen here with the 5-number summary? I'm expecting the median to be closer to the first quartile than it is the third. That's what we're expecting here. Remember we talked about that with the box plot? With the 5-number summary, what do I want? If the median should be closer to the first quartile than it is the third, I'm seeing the right skewness. My summary is telling me that also. And then, like I said, 2.46, these are side-by-side box plots. It's really similar to the one we did on Tuesday in class, at the beginning of class on Tuesday, and I think I did 2.47. You're going to give me some side-by-side box plots. You're going to have how much people spent in a restaurant when they had a lavender odor, a lemon odor, and no odor. And you're going to want to see about the spread. Is there any skewness there? Did they spend more with one of the odors than the other odor? Okay, that's that type of question. You have the same quantitative variable measured on 3 different groups. Lavender, lemon, no odor. The variable you have measured, if I remember right, is the amount spent in euros by customers in a restaurant when exposed to the orders. I'm looking at table 2.2 on page 72. That's all for Tuesday. Now, back to chapter 3. Now, you notice tonight we went through the homework problem. Anywhere there's a question mark in the homework, answer that question. Because some of those, like the one number 31, 2.31, there's like a part A, but there's like 4 questions in there. You've got to answer all the questions. Okay? I didn't really look at the homework that people have been sending me yet to see if you're answering all the questions, but I'd warned you about it before. I'm warning you about it again. All right? Now, where we left off on Tuesday was the last thing I wrote up was we're in chapter 3, and it's called the normal distributions. I talked about exploring a distribution, interpreting a histogram, and I gave you 3 things we've already been doing in your notes. Right? We plot your data, histogram or stem plot, because we have a quantitative variable. We tell about the overall pattern, shape, center, spread, right? Possible outliers, anything that's a striking deviation. We added numerical summaries for the center and spread. How do you calculate center? How do you calculate spread? Look, that takes us through the first 2 chapters. Chapter 1 was the graphs, and chapter 2 was the center and spread, right? And then there's a new one, and this is chapter 3. The pattern you're seeing, the overall form, the overall pattern you're seeing in your histogram is so nice, it's so regular, you can see it so good that we can describe it by a smooth curve. In other words, we can draw a smooth curve in that approximates what you're seeing in the histogram. Okay? Now, this smooth curve has a name, and it's called a density curve. That's what we're interested in this chapter, something called density curves. Now, what I want to look at is I want to look at example 3.1 here to show you where we're headed in this idea of somebody drawing in a smooth curve that approximates what you're seeing in a histogram. So this example 3.1, what they have is this. All right? It says, our eyes respond to the areas of the bars. Wait. Look at figure 3.1 for a second. Histogram of the Iowa test vocabulary scores of all 7th grade students in Gary, Indiana. The smooth curve shows the overall shape of the distribution. Now, what I've got is this. I've got 947 7th graders. Yeah, they're in Gary, Indiana. Okay. And what I have is, yeah, it's a vocabulary part of the Iowa test of basic skills, vocabulary scores. So I'm just going to say what I have measured here is test scores. This is not the first time we've looked at this histogram. We looked at it back in chapter 1 when I showed you a picture of the first one that was roughly symmetric. I can't remember what the example was, but it was back in chapter 1. Okay? Now, if I was to look at that histogram for a second, what's its shape? Right? So I'm looking at the histogram. And I'm looking at the histogram, and it's figure 3.1. What's its shape? It's roughly symmetric, isn't it? Single peaked. Unimodal. Now, I'm not going to say anything about center and spread, because just looking at it, at this point, I'm not going to eyeball any center and spread for you. Is there any outliers? So, I've done half of describing what you're seeing in that histogram, right, or describing the distribution. I know it's roughly symmetric, a single peak, unimodal. I don't really see any outliers there. Obviously, the center's right in the middle somewhere, and the spread goes from the smallest to the largest, right? If I was just looking at it, eyeballing it. Now, I want to look at example 3.1. Our eyes respond to the areas of the bars in the histogram. Remember, the height of the bar is supposed to tell you how many of these 947 seventh graders fall in a particular class, right? That's what it does. The height of the bar tells you how many or the percentage. This is telling you, I'm hoping this is how many, it might be the percentage. It says, the bar area represents proportion of the observations. Is that true? All right. You understand that when I look at all the area of the histogram, that's all my individuals in the data set, right? It's all 947 of them. Yes? If I'm looking at all that area represents total area being 1, right? There's 947 out of the 947 represented. You give me any single bar, and I find out how many is in that particular class, how many is represented by that bar, and I divide by the total number. Is it giving you the proportion that fall in that class? And the answer is, yeah. Okay? It says, figure 3.2a on the next page is a copy of figure 3.1 with the leftmost bars shaded. Now, I've got figure 3.2a. And I'm interested in the histogram at this point. I know that you can see the smooth curve drawn there, but I am interested in the actual bars. And it says it has the leftmost bars shaded. If you notice, it has shaded a score on this test 6 or lower. right? That's what we are representing here. With those ones that are shaded in whatever color that is, orange or whatever color you want to call that, we have shaded from 6, right, 0.0 or lower, right? So those bars represent the students that scored 6.0 or lower on this test, okay? Now, the book is going to tell me, because, look, I don't have a y-axis to read the height of the bars here. They're going to tell me there are 287 students. In other words, you have 287 students that scored 6 or lower out of the 947. Look, you've got to give me the benefit of the doubt. I don't have a scale to read the heights. If I would add up to all those heights there, I better add to 287, right? That's what they're telling me. You know, all the bars I have shaded, the heights represent how many fell in that particular class. If I add all those heights up, they're telling me there's going to be 287 students represented by those bars. Well, what's the proportion of students that scored 6 or lower? If you take 287, divide by 947, why 947? That's all of them in the histogram. That's all the individuals you have. That equals a proportion of, what do I get here? What does it tell me? 0.303. Now, if I take 287, divide by 947, I get a proportion of 0.303. Now, I'm going to be honest with you. You guys don't want to hear about a proportion. People don't report proportions. What they report is move the decimal place to the right. If you've got a proportion, multiply by 100. What this is telling us is in this histogram, 30.3% of those 7th grade students scored 6 or lower. All right, don't look at me like I'm talking Greek to you. You just turned in homework problems to me, back out of chapter 1, and I can't remember if it was 1.26. You had a STEM plot. Remember? You had IQ scores in some Midwest place. You had 78 of them, STEM plot. Didn't one of the questions ask you what percentage of the students or the IQ scores was above 100? Did that question? You just turned it in to me. You asked me that, right? How'd you do it? You added up all the ones that was 100 and you divided by 78, didn't you? Am I doing the same thing here? I know I don't have the little leaves and all that crap, but I'm telling you how many are represented by the bars, and I'm telling you there's 287 of them scored 6 or lower. You're dividing by the total number and give me the percentage 30.3. You just did that with the IQ scores in the STEM plot in chapter 1. Yeah? That's what you did. That's how I'm doing the same thing. Instead of being above 100, I'm 6 or lower. Right? If you wanted to shade that little STEM plot, hell, you'd have just colored them little numbers in blue or something and said, okay, those represent above 100. All right? That's exactly what I'm doing here. Now, look, you have to understand that when I'm giving you homework problems, I didn't just go through and say that one, and that one. No, I knew this is coming. Well, hell, you just did it. Okay, it was a STEM plot and not a histogram. The STEM plot, hell, I can see the pieces of data. The histogram, I see the heights of the bars. Right? Same guy, same thing. Yeah? Okay. Now, that's chapter 1 stuff. Right? Oh, let's see. What bars represent what you're talking about here? 6 or lower. Oh, it's all those. Add them up. 287 of them. Yeah? Now, we get to chapter 3. We want to deal with that smooth curve. So now we look at figure 3.2b. Now what is shaded is not, and I repeat, is not the bars in the histogram, but what's shaded is that area under the curve. Right? Now I'm going to do this. You're focused in now on the curve. Before it was the histogram. Now it's the curve. They've shaded 6.0 or lower. Right? Not the bars, the area under the curve, right? Everybody agree with that? You see the difference. There's some little purple of the bars sticking above the curve there. They shaded under the curve. Now, it says, now look at the curve drawn through the bars. Figure 3.2b page 77. The area under the curve to the left of 6.0 is shaded. Everybody agree? That's 6.0 or lower. Yeah? We can draw histogram bars taller or shorter by adjusting the vertical scale. Is that true? Instead of going by 2s, I could have went by 5s. Or I could have went by 1s, right? And I could make the bars do this. They still represent the same number. It's just I changed the scale to make them look taller or shorter, right? Now, in moving from histogram bars to the smooth curve, from approximating a histogram with a smooth curve, we make a specific choice. We adjust the scale of the graph so the total area under the curve is exactly 1. Now look, everybody looking at me? Everybody look up for a second. I ain't changing shit. When I draw you that smooth curve, the area under that curve for us always represents the area of, I don't care which one I draw. And I tell you, this is your curve, the total area under it is. Why? Because that area represents a proportion of, which represents a percentage of 100%, which represents all the observations. Just like all the bars in the histogram has an area of 1, a proportion of 1, represents 100% of the observations, that smooth curve does the exact same thing. Area is 1, proportion of 1, percentage of 100%. Now, there's a reason why I did this, because now when I start looking at these smooth curves, I'm going to use 3 words interchangeably. Area, proportion, percentage. And if I throw a 4th one in there, just write one of these other 3. Okay? We're interested in areas under the curve because the area represents a proportion of observations, just like with the histogram. If you have the proportion, you have the percentage, move the decimal place 2 to the right. And that's what they're going to tell us here. The total area represents the proportion of 1. That is all of the observations, all 100% of them. The curve is now a density curve. The shaded area under the density curve in figure 3.2b represents the proportions of students who scored 6.0 or lower. That's what you shaded. That's what that area represents. It turns out that area is, now I can't show you where they come up with this, 0.293. So that area in 3.2b that is shaded under the smooth curve, the density curve, to the left of 6.0 is 0.293. What's the percentage now? That is 29.3% of the total area, which is 100% or a proportion of 1. We have to take it on their word that that area is 0.293. I can't do anything. I can't show you that yet. It says only 0.01 away from the actual proportion from the histogram. The method for finding the area will be presented shortly. It's the rest of the chapter, folks. For now, note that the areas under the density curve give quite good approximations to the actual distribution of 947 test scores. With the density curve, we got 29.3%. With the histogram, we got 30.3%. Is that a good estimate? You're off 1%. The point is, you're not losing anything trading in the histogram for your density curve. That's the point. Right? Now, here's the thing. Sometimes I worry about how much I tell you at a particular point in the semester. I'm going to tell you the truth here. Okay? The histogram represents a set of data, right? You had 947 7th graders in Gary, Indiana, and you had their test scores. You make the histogram, you would have made it in Chapter 1. The density curve is you're following the histogram and you're approximating what you're seeing. The area is telling you that we just came up with in this example here that it's a pretty good approximation. Now, I'm going to be honest with you, all right? The histogram always represents a set of data. You got the data listed for you, you make the histogram. The density curve, other than it being a good approximation to what you're seeing in the histogram, as far as areas go at this point, it's representing all 7th graders, not just the 947 in Gary, Indiana. All right, everybody look at me again. Yeah, we're going to do this a couple times tonight. when you have the data in hand, it's from a larger group of individuals, right? I mean, you can think about all these. Remember when we did the North Carolina travel times and there was only 15 individuals? You understand there's more people than 15 in North Carolina to have travel times to work, isn't there? Remember we had 20 travel times to work in New York? You know there's more than 20. We're just taking a small chunk out of everybody, right? And you can make the histogram or the stem plot. As soon as you start drawing in the smooth curve, you're looking at all travel times in North Carolina or all travel times in New York. Just like here, you're looking at 947 7th graders in Gary, Indiana for the histogram. But as soon as I draw that smooth curve in, that density curve, now we're looking at all 7th graders. The book's not going to tell you that story right at the moment. But I got to give that to you because I don't want you to think, shit, he's just throwing away the histogram and he's drawing in this smooth curve. What's it represent? It's giving you a feeling for what the histogram looks like, but it represents not just the 7th graders, 947 of them. It represents all of them, right? So there's something else going on here, okay? Now, I'm on page 77. There's a little box there. I'm not going to write it. There's a definition. A density curve is a curve that is always on or above the horizontal axis, right? Your x. It's always on or above. 2, has area exactly 1 underneath of it. We had that talk, didn't we? That area is going to represent a proportion of 1 or 100% of the observations. Anytime I draw you a density curve, you'll see it's on or above the x-axis, the horizontal axis, and it's always going to assume to have area 1 underneath of it. Okay? It says, a density curve describes the overall pattern of a distribution. In other words, what they're telling you is, if your histogram is roughly symmetric, the density curve that you draw, that is drawn for us, will be roughly symmetric. If your histogram is skewed to the right, your density curve will be skewed to the right. If it's skewed to the left with the histogram, the density curve is going to be skewed to the left. Whatever the shape of your histogram or stem plot is, and it's usually a histogram here, the density curve has the same shape, right? It is following it. So you're not going to lose anything, right? You'll have the same overall shape. Now, here's what I want to do. If I draw this, what's that shape? That's my favorite roughly symmetric histogram, isn't it? Now, anybody got any feel for what the... Look, I'm going to draw it. That's a density curve. What's its shape? If you cut it in the middle and fold it on itself, the left-hand side would lay on the right-hand side. That is a symmetric density curve. What's the area under this density curve? Thank you. I heard somebody tell me the area is 1. Why? Because I used the word density curve. Okay? So that's how we're following there. I'm going to do one more here. What about if we got something that you're looking at a histogram and it is skewed to the... That's my favorite one. What's the density curve going to look like? Has that density curve got a tail going out to the right? Yeah. The density curve is going to be skewed to the right. What's the area under this density curve? I don't care what the shape is I draw for you. If I tell you it's a density curve, the area under it is always 1. Represent a proportion 1. It represents 100% of the observations. Now, if it was skewed to the left, we'd have the tail going out to the left. So in other words, when you're telling me a density curve skewed to the right, it's got a tail going to the right. Skewed to the left, it's got a tail going to the left. Roughly symmetric, fold it. Same as I told you for a histogram back in chapter 1. I didn't change. Are you shocked I'm not changing? No, I don't have to change because what's the histogram there? What's the density curve there for? It's to approximate your histogram, right? So there's no way you're going to have a histogram that's skewed to the right and your density curve is going to be roughly symmetric. That's not an approximation, right? You shouldn't lose anything like that. Now, what about describing density curves? Translation, a density curve has measures of center and spread. Just like a histogram, you can measure center and spread. A density curve, you can measure center and spread. Okay, let's start with the median. In a histogram, how do we find the median? In half smaller and half larger? Half smaller. Half larger. It's the 50-50 area point. That means half the area is to the left and half of the area is to the right. Half the area is larger than its value, half the area is smaller than its value. Look, you guys are writing this down like I'm telling you something new. I told you the same crap back when we were talking about a histogram. Now, obviously, when we did it before, we actually calculate the median, right? Put them in order. You're just going to eyeball the median. Where's this 50-50 area point? Okay? Now, what goes along with the median? It's always the quartiles, right? What do you think they do here? They divide the area into quarters. Just like the quartiles of a set of data divide the data into quarters, the quartiles of a density curve divide the area of that curve into quarters. Okay? Now, the mean. Yeah, I know. When we have the data and we have the histogram, we add them up and divide by the total number. Well, here, the mean is the balance point of the density curve. Think about it like this. The density curve is made of some solid material. And the point where it will balance will be your mean. Right? Now, do you remember we had a talk about how the mean and median were related to each other depending on the shape of the histogram? I'm getting ready to have the same talk with you about, depending on the shape of your density curve, how the mean and median are related. It's going to be the same exact thought. So if I'm looking at the particular shapes that we like, okay, now I'm going to do away with the word roughly on symmetric, because when I'm drawing you a symmetric density curve, remember I smoothed everything out, it's going to be symmetric. So if I look at symmetric, what do you expect the relationship between the mean and median to be? Where's the 50-50 area point if it's exactly symmetric? Dead in the middle. Where's the balance point? Dead in the middle. If it's exactly symmetric, I expect the mean to be equal to the median. If it's skewed one way or the other, what always happens to the mean? It gets pulled further out the tail, right? The mean is pulled further farther out the tail. Than the median. Now, before we go any further, all right, I'm going to draw you a couple pictures. Okay? You have to get used to the fact that I'm done drawing histograms for you. I'm very interested in these density curves. Right? These smooth curves that approximates what you would see in a histogram. All right? So The other thing is, when I draw you this smooth curve, I do not need the y-axis. Like, I don't need heights of bars. There are no bars. So you won't even ever see me draw a y-axis now. Remember, on the x-axis still goes the value of the variable, right? That's still the variable down there. Your quantitative variable is on the x. I don't need the y anymore, right? Because I'm not reading heights. So if I draw you one like this, that's roughly symmetric, right? Actually, that's exactly symmetric. Where's the mean? Where's the median? I'd expect if I cut this in half, if I could fold it, the left-hand side lays on the right-hand side. That makes it symmetric. This is the value of the mean. That's the value of the median. While we're here, what's the area under this guy? I got to ask that a couple times because I'm trying to get that stuck in your head. When I draw one, I'm not rescaling anything. The area is always assumed to be 1 under it. That's what makes it a density curve. Now, one more. If I drew one that looked like this, what would you tell me that one is? That is skewed right. I have a tail going to the right. What do I expect the relationship between the mean and the median to be? Now you understand the median's got to be somewhere here. The mean gets pulled further out the tail. The mean is going to be somewhere there. Go back to when we talked about this with the histogram. I drew you the same pictures with histograms. Instead of it skewed to the right, the mean gets pulled further out the tail, so the mean was greater than the median. What's skewed to the left? The mean will be smaller than the median. That is the balance point. The median is a 50-50 area point. Half of the area is smaller, half of the area is larger. Now, one more thing before we get to the title of the chapter, the normal distributions. When we are talking about data, does everybody understand what I mean? I'm back to chapter 1 and 2, and I have the data in hand, and I'm looking at a histogram, right? I got all the individuals, I got the values of the value of the variable for them. Anytime we had the mean, we used x bar. Remember, that was our notation. For the standard deviation, we always used s. That's our notation out of chapter 2 for the mean and standard deviation, where you have the data and you calculate it, right? Whether we put it in the calculator and calculate it, whether we put it in the Minitab and calculate it, that was our notation. That's how you know you're always talking about the data. If somewhere in the book somebody's talking to you about an x bar, they had the data and they calculated. Or they talking to you about the standard deviation s, they had the data and they worked with it. They found the standard deviation. When we make the jump from the data and the histogram to the density curve, a density curve has a mean and a standard deviation. Now, remember, the density curve is approximating what you are seeing in the histogram. We cannot use x bar and s. That's from the data and from the histogram. So for the mean, what we use is, that is mu. The Greek letter mu. It's kind of a funky u. And for the standard deviation, what we use is, that is the lowercase sigma. So in our book, anytime somebody's talking to you about the mean mu or the standard deviation sigma, they're not looking at the data. They're not looking at a histogram. They are talking to you about a density curve that we want to look at. Now, here's my question. You got to understand this point. I have a histogram, and the density curve is approximating it. Do we expect mu to be equal to x bar? Do you expect the mean of your density curve to be equal to the mean of the histogram? And the answer is no. If we did, we'd use the same notation. Do we expect it to be close? Yeah, you're approximating, right? In other words, if x bar is 26.7, I wouldn't be shocked to see that mu is 25. I don't expect, if your approximation is any good, x bar should be close to mu, and S should be close to sigma. I don't expect them to be the same when we are approximating what you're seeing in a histogram with a density curve. Okay? Go back to this. Remember I told you the histogram represents some small group out of everybody you're looking at, whether it was North Carolina workers, New York workers, or 7th grade students? Those were X bars and S's, right? And then when you're looking at all North Carolina workers, all New York workers, or all 7th graders, there's no way I expect the mean from these 15 or 20 or 947 to equal the mean of all of them. But if my approximation is any good, I expect it to be close to what's going on with everybody. All right? Now, we are interested in a particular type of distribution and a particular type of density curve. And what we're interested in is normal distributions. Remember, that was the title of the chapter. The first part of the chapter is just getting your head around the fact that we're getting ready to get rid of the histograms, and we're going to work with these smooth curves, these density curves. Now, normal distributions all look the same. Okay? They're all symmetric. Single peaked. Look, I know at this point I'm supposed to come out there in parentheses and write unimodal, but that's not what rings in my head. It's symmetric, single peaked, bell shaped. Those are the three things I think about. Symmetric, now, they are described by what we're going to say are normal density curves. They all appear the same. Normal distributions. What somebody tells you is your variable follows a normal distribution, right? Whatever quantitative variable we're looking at, it follows a normal distribution. So we know the density curve that's going to represent that distribution is going to be symmetric, single-peaked, and bell-shaped. They all look the same. Those ones that are symmetric, single-peaked, and bell-shaped, they are described by, they are called normal density curves. Normal density curves describe variables that have normal distributions. They have a particular look to them, all right? Symmetric, single-peaked, and bell-shaped. Now, they all have the same shape. I said it, now I wrote it for you. They're all symmetric, they're all single-peaked, and they're all bell-shaped. Now, there are many normal curves that describe normal distributions, right? So depending on what variable we're looking at, and somebody tells you, oh, this variable has a normal distribution, we have to know what normal curve represents that normal distribution, right? What curve are we going to draw? So you choose a particular normal distribution, right? How are we going to pick out the one we want to work with? By giving its mean and standard deviation. And I apologize for not putting in there the mean and standard deviation. What normal distribution are we looking at? What normal curve are we looking at? You tell me what one you're looking at, because I know the shape. You tell me its mean as the center, and the standard deviation of telling you about its spread, right? Remember, mean still measures center, and standard deviation still measures spread about the mean, right? So you pick out a normal distribution by telling me it's mean mu and its standard deviation sigma. My notation for this is, I'm not going to write it out for you every time that we have a normal distribution. My notation is normal, mean mu, standard deviation sigma. So what I'm telling you is a normal distribution has two unknowns, two parameters. It's mean mu and its standard deviation sigma. Once I get those from the problem, I know everything I need to know about that particular normal curve that describes that normal distribution. Okay? Now, the mean is the center. The standard deviation is measuring the spread about the center. All right? Now, mean is the center. Okay, what's every normal curve look like? They're symmetric, single peaked, and bell-shaped. They look like this. Where's the center? Where's the mean? It's symmetric. It's right in the middle, right? I mean, it's also the median, but we're interested in the mean at the moment. So here's what happens. If you start changing the mean, what you are changing is the location of your density curve. If the mean is 10, it's centered at 10. If the mean is 50, it's centered at 50. If the mean is minus 22, it's centered at minus 22. The mean is the, look, you understand right here? This little guy here, go all the way back to your histogram. Hell, that's the x-axis. That's the value of the variable there, right? This is your x-axis. The mean is the locator. Where is the density curve? Well, hell, it's centered at 10 or it's centered at 50. It's centered at minus 30. It's just telling you where it is. Changing the mean just slides the density curve. That's all, right? If you go from 10 to 30, well, you just pick it up and it was centered at 10, now it's centered at 30, right? That's what the mean is doing. It's the locator on the x-axis. Where is it centered? Okay? Now, the standard deviation. Controls the spread. Now, I'm going to be a little technical with you for like 3 minutes. Okay? So, when I draw you a normal curve, you know, it's just like the best thing I draw in this class, right? The drawing of those is actually better than my handwriting. Do you know how many of these we draw throughout the semester? This is our favorite. These are our favorite density curves, are these normal curves. We know the mean is right here, correct? Right in the middle. Okay? Now, I can get a feel for what the value of the standard deviation is. I'm not telling you you're going to read it exact. You've got to give me this, and I'm going to draw you two pictures, one on top of the other, and then I'm going to ask you something about the standard deviation. The standard deviation is this distance right here. If you will notice, you see how the curve is like curved down here? And then at this point here, it looks like it starts to curve back up. If you had count 1, that's a point where the concavity changes. Some of us hadn't. What I'm telling you is there's a point there where, you know, you're curved down, and then it starts to turn and curve back up. So whatever that little point is there, okay, you come down here right below it, and you look at this distance from here to here, that's your standard deviation. No, I'd never give you anything like that and say, well, tell me what the standard deviation is based off of this density curve. My point is, the larger the standard deviation is, the flatter your curve is and the more spread out things are. The smaller the standard deviation, the taller that hump is, and the more things are clumped in on the mean. Because what's the area under that density curve? Right? So the standard deviation might change, and what it does is, when you start decreasing the standard deviation, I got my hands on the side of that density curve, right? And I'm pushing in. So what has to happen? The total area stays 1 all the time. As the standard deviation gets smaller, I'm pushing in. What happens? That hump's getting taller, right? and everything's getting closer. As I make the standard deviation larger, the hump gets smaller, and I'm starting to spread things out, right? Because the total area stays 1 no matter what the standard deviation is. Okay? So the standard deviation controls the spread. The smaller, the taller your peak is. The taller your hump is. The larger, the flatter it is. Are they still symmetric, single-peaked, and bell-shaped? Yeah. Okay, let's do this. I'm going to draw you one here. I'm going to draw you another one down here. They both have the same mean. Okay? What's the area under both of them? Which one has the larger standard deviation? Which one has the more spread about the mean? You understand why? It's not as tall and it's more spread out, right? Which one has a smaller one? Well, look, there might be a homework problem somewhere in here where it says they give you like little numbers and they ask you to estimate the standard deviation. You're not going to hear that from me. I want you to understand that. The larger the standard deviation, the flatter it is, the more spread out it is. The smaller the standard deviation, the taller it is, and the more pushed in it is. Think about it like this. The smaller the standard deviation, the smaller the spread, the closer the observations are to the center. The larger the standard deviation, you got some that are further away. Okay? Because the area is always 1. That's how I think about the standard deviation. So here's the deal. The mean controls where it's located. Yep. The standard deviation controls how tall the peak is. It doesn't matter where it's located. It doesn't matter how tall the peak is. The area is still only 1. Does that make sense? Okay? Now, all that little story I just told you is on the bottom of page 81. About, a normal distribution, the mean and standard deviation, the mean's the center, standard deviation spread, and that little part there about clumping in or pushing out. Pushing it down or pushing it up and pushing in. Okay? Now, we're interested in these normal curves. We're interested in these normal density curves. We're interested in these normal distributions. All right? Now, the rest of this chapter has one thing in mind. Is give me a variable that has a normal distribution, that its distribution is described by a normal curve, symmetric, single-peaked, bell shape. It has a mean and standard deviation. Let's find the area under one of these normal curves. Right? We're interested in areas under normal curves the rest of this chapter. Because remember, the area represents proportions of observations, and if you got the proportions, then you have the percentages. All right? So, we come to page 82. I'm assuming you guys might read the book some. I don't know if you do. People always want to know, so why in this class are we so interested in these normal distributions? Well, they play a role in 3 places for us. One, it turns out there's a lot of variables that we look at that are actually studied that follow a normal distribution, that are described by a normal distribution. 2, what's the title of this class? Statistics and probability. The normal distributions play a role in probability that we're going to study, right? 3, at the end of the semester, we're going to do 6 or 7 chapters where we're interested in some large group, like all North Carolina workers' travel times, but you can't deal with all millions of them, so we deal with a smaller group. And then we want to take what we learned from this smaller group and infer back to the larger one. Normal distributions play a role there too. So the deal is this. They show up in Chapter 3. They show up again in Chapter 10. And then when they show up in Chapter 10, they don't go away the rest of the semester. All the kind of calculations and work we do are always with normal distributions. Okay? Now, our first go at finding area under the curve is something called the 68, 95, 99.7 rule. Now, I'm going to be honest with you at this point, because like I said, I always am. What makes a symmetric, single-peaked, and bell-shaped curve actually a normal curve it satisfies this rule. All normal distributions satisfy this rule. Now, your little rule, this 68, 95, 99.7 rule is in the middle of page 82. And here's what it says, and I'm going to draw you a picture of what it says. That if you have a normal distribution, and you have the mean in the center, and if you go one standard deviation on either side of the mean, then that area that's under the curve between those two values down here is 68% of the area. If you go two standard deviations on either side, that area under the curve between those two values represents 95% of the area. Any idea what 3 is? That's the 99.7 part. So, before I give you an actual problem, what's written out here is this. If you give me a normal distribution, remember the two most important things you can ever tell me about it is its mean and its standard deviation. We know what it looks like. It looks like this. Right? They all look like that. And so the 68 part of the rule says, if you come over here and you take the mean and you go one standard deviation to the right, greater than, and one standard deviation to the left, and you look at this area under the curve between those two values, this area here is 68% of the total. If you like, the proportion of area you're looking at is 0.68. I talk about it in terms of percentages, right? Move the decimal place. 68% of the area is between those two values. In other words, 68% of the observations fall within one standard deviation on either side of the mean. Now, just because we know that, we know more. So, in red there is 68%. How much is out here? And how much is out here? Let me ask you this. If there's 68 here, how much has to be total outside? It's 100 minus 68, right? It's everything that's left over. There's 32%. Is things nice and symmetric here? Doesn't there have to be half of that 32 and half of that 32 here? This has got to be 16. You know more than just the 68 part. Oh, I know there's 16% out this tail, there's 16% out that tail. And while we're here, how much is here that I got in blue? If there's 68% between them, the mean's right in the middle, and if I want from mean 1 to the right, that should be half of the 68, shouldn't it? This should be, the blue is, so you know a whole bunch of crap, more than just one on either side or 68%. We know a bunch. Using the fact that there's 100% of the area under there, and everything's nice and symmetric. Now, I would like to do the 95 part also, because that's where you go 2 away. Okay? So, again, give me any normal distribution you want. Tell me what its mean is. Tell me what its standard deviation is. Then, if you're telling me that, it looks like this. I draw them all the same. Here sits your mean. If you come out here and go the standard deviation, 2 times the standard deviation to the right, that just means 2 sigma plus mu, and mu minus 2 sigma. So that's 2 standard deviations to the right, greater than the mean, 2 standard deviations to the left, smaller than the mean. And if I look at this part here, remember that area represents proportions of observations, percentage of observations. The little rule says that that area represents 95%, right there in red. In other words, 95% of the observations have a value within 2 standard deviations of the mean, either direction. Remember, we're reading things off the x-axis. That's values of the variable. The area is just representing proportions of observations or percentage of observations for you. If there's 95% that I have there, how much is in the tails? How much is left over? What's left over is 5. There has to be half and half. So out here, there must be 2.5%. And out here, there must be 2.5%. So that I know 2.5% of the observations are less than 2 standard deviations to the left, right? And I know 2.5% of the observations are greater than 2 standard deviations to the right of the mean. Okay, what was the other one I just did? Let's do this side. What should this blue be? Before I took half of 68, right? It should be 47.5, right? It should be half the 95 in blue there. How's the 99.7 work? Well, draw yourself the picture, go 3 on either side. Between them, there's 99.7%. What's actually left on the outside? This time, it's 0.3%, right? So it must be 0.015% and 0.015%. There's very little in more than 3 away. Yep. Remember, it's 99.7 is 3 either direction. You take 100% minus 99.7, and you got 0.3%. So it's 0.015, 0.015. I'm sorry, 0.15. 0.015. Now, can we stick some numbers to this? Students usually hate when I just start drawing pictures and all I got symbols, especially Greek symbols, right? So then we come to a problem like example 3.2. Put some numbers to this. So what I've got here is, they're going to tell me a little bit about these Iowa test scores. You know, the ones we were just talking about at the beginning of Chapter 3. It says figure 3.1 and 3.2, pages 76 and 77. We talked about them. I showed them to you. Shows that the distribution of Iowa test scores, vocabulary scores for 7th grade students in Gary, Indiana, is close to normal. Now, warning. When somebody tells you in this class it's close to normal, that means normal. Okay? So, they're telling me I'm looking at these test scores. I'm just trying to remind myself what the variable is. They're telling me it's normal. Now, the reason I wrote that little in there, as soon as somebody tells you that your variable that you're looking at has close to a normal distribution, you're looking for 2 things now. The 2 most important things you can tell me about any normal distribution is its mean and its standard deviation. That's what I'm trying to look for here in the problem. It says, suppose that the distribution is exactly normal with a mean of 684, 6.84, and a standard deviation of 1.55. Now, folks, I know everything I need to know about those Iowa test scores. I know where they're centered, and I know their standard deviation. I know their mu, and I know their sigma. Right? Look, you guys have done some homework problems, right? Well, you turned them in. You do understand that every question in this class is a word problem? Oh, there's no 2x is equal to 4 and solve for x shit here. Everything's a word problem, right? So you have to be able to pick out the information. That's the hard part, is picking out the information out of the problem. So my warning is, as soon as somebody tells you you're looking at a variable and it has a normal distribution, you better be finding mu and you better be finding sigma. It better be in the problem somewhere, and then we better write it down. Now, you notice I wrote that stuff down. I don't even know what the hell they're going to ask me to do. Because I know as soon as you tell me it's normal, if I don't know these, well, it don't matter what the question is, I can't answer. And please, stop skipping over words when you read. You do it. I know. All of you do. It's not like I'm not being mean about it. I'm just telling you, stop. Read everything that's there. Now, when I read the problems to you, you see me skip over stuff? No. The hell, you might miss the important part. Now, the reason I say that is because I've had students on tests say, I don't understand the question. So instead of me explaining the question to you, I ask you to read it to me. they read it to me, damn, they're skipping over the important shit that you need to know, right? Read all the words. It's okay. It takes an extra second. Read them all. So here's what it says. It says, these are the mean and standard deviation of the actual 947. Figure 3.10 applies the 68, 95, 99.7 rule to the Iowa test scores. Now, if you don't mind, since the 95 part's done for you in this example, right, they're going to go 2 standard deviations. Can we work on the 99.7 part? Just so I can show you something a little different, how I would handle the 99.7 part. They're talking about the 95 part, okay? Now, remember, this is, yeah, that's standard deviations. There's 3 standard deviations either way here. So, when I get here and I draw you this picture, I know it's normal. I know where it's centered. Right? The mean there is 6.84. Now, what does it mean to go 3 either way? It means there's a point out here where you take 6.84. Somebody got a calculator today. Well, we can just look in the book. I'm sure they got it there somewhere. And take 3 times 1.55. That's 3 standard deviations to the right. So 6.84 plus 3 times 1.55. If you do that, you get 11.49. So that value is 11.49. That's 3 standard deviations greater than the mean. And then if I want this other point out here, where I take the mean 6.84 minus 3 times 1.55. 2.19. So here's what we know. That if you went 3 standard deviations on either side, 3 to the left, 3 to the right, that area represents 99.7% of the area. That's a lot of the area, right? All that's left is 0.3%. Now, here's the kind of statements we want to think about here. Yeah, I mean, I know I got the picture and I'm drawing you that. And look, I could have done the 95 part or 68 part. Does everybody understand how I came up with these values here? Right? You're interested in the 99.7 part. That's 3 standard deviations. I took your mean. I added 3 times the standard deviation. I took your mean and I subtracted 3 times the standard deviation. So what this is telling me is 99.7% of the test scores are between 2.19 and remember the area, that proportion, that percentage is representing observations. So as soon as I'm talking about 99.7% of the area, I'm talking about that area is representing 99.7% of the observations. So what that means is 99.7% of the test scores, which is what your observations are between 2.19 and 11.49. Okay? Now, I'm going to come back to this picture here because I want to make like another statement for you. How much area is out here? Well, what's left over is 0.3, right? 0.3 divided by 2 is? Is that correct? Yeah. So looking at that, now I'm not going to do the one to the right. Obviously, the one out here to the right is also 0.15%. Can I make a statement here? Well, yeah. I can also read off of here based off of that 0.15% of the test scores are less than See, we got to get the interpretation of what's going on here when you're looking at this area. Right? So 0.15% of the test scores are less than 2.19. And again, remember, I can tell you all kinds of things here, right? Because you know more than just between or the tails. You know from the mean down here, the mean of there. We know all kinds of things, right? So I just wanted to make a couple statements here to say, how do I use this kind of stuff? How is this going to play a role in the future? Well, the area represents proportions or percentages of observations. And I know we're looking at the area under the curve. You're really talking about the values here, right? The 2.19 and the 11.49. Okay? Now, I'm not going to get real carried away here with the a lot of these 68, 95, 99.7 rule. Okay? And the reason I'm not is, suppose I want to know the following here. Okay? Suppose we're looking at these Iowa test scores, right? The Iowa test scores. Well, out of this example, we know they follow a normal distribution with a mean of 6.84, and a standard deviation of 1.55. Everybody agreeing with me there, right? The hell, I'm just reading that out of the example. Now, what I want to know is, instead of just saying, okay, give me some 2 or 3 away, the questions come like this. What percentage of scores are less than 5.29? Okay, so we know the 68, we know the 95, we know the 99.7 part of the rules. Here's the way the questions work using that rule. Now, here's the first thing I do. You're going to see me do this today, and then on Tuesday, we're not even near being done with this chapter here. We're going to work some problems, and I like to take the questions, I like to turn them into symbols. See, because what I want here is, and I always use big capital P. You're going to see me use that big capital P if somebody's talking about area under the curve, proportion under the curve, or percentage under the curve. And I always like to write out what that question is. See, I want the percentage of scores that are less than 5.9. And I always use X for whatever variable it is. You know, we're talking about Iowa test scores. That's my X. I want the percentage where X is less than 5.29. Look, that's nothing more than me translating the English into symbols. Okay? This is my question. This is what we want to answer right here. All right? So my next step is I draw you the normal distribution that we're working with. Remember, it is centered at 6.84. Remember, it's normal, centered at 6.84, standard deviation of 1.55. And then what I'm going to do is I'm going to take the value that's in my question. You'll hear me say, I'm going to take the value that we are interested in. We're interested in something about 5.29, correct? So I'm going to put 5.29 on my picture. Now, you understand, that's the x-axis, right? So 5.29 needs to be to the left of 6.84. 5.29. Then my next step is, I always draw a line from the curve down to that point I'm interested in. That value of the variable that I'm interested in, 5.29. And then for a couple times, I'm going to ask you a dumb question. Which way do you want to shade? What area do you want? Do you want the area to the left, or do you want the area to the right? And I'm hoping everybody understands we want the area to the left because we want the percentage of scores less than 5.27. So I want this area right here. You see this part right there? That's telling you where to shade. You're shading to the left. Now, hopefully, with what we know now, 5.29 is either 1, 2, or 3 away. If it's not, you're not going to do this problem, right? So if you'll notice that 5.29 is 6.84 minus 1.55. Is that true? So what is that telling me? It is one standard deviation smaller to the left of your mean. Everybody agree? What do we know about being one standard deviation on either side? Is that the 68 part? So what do we know? One to the left and one to the right has 68. Yes? How much has to be left over is the 32. So what's the area I got shaded there? Oh, I said a lot without writing anything, right? Okay, hang on. No, I'm going to put some red here just to show you what I did. Because here's what I know. If I got 8.39 here, then this area here is the reason I'm interested in the 68 part because I'm interested in the value of the variable 5.29. And it was one standard deviation to the left. I know one to the left and one to the right is 68. There's got to be 32 left outside, half and half, 16 and 16. 16% of the test scores are less than 5.29. That's how the problems work with the 68, 95, 99.7 rule. It's not like somebody starts and says, okay, give me all of it. No, there's a particular question you're trying to answer. And so I get this. I always like to come back and write my answer. My answer is 16%. 16% of those test scores, those Iowa test scores, are less than 5.29. Now, here's the warning. If you are 1 away, 2 away, or 3 away, we can answer these kind of questions. If you are not 1 away, 2 away, or 3 away, we got to come up with a different method. That's going to be Tuesday. Now, here's what I want to do before we get home. I got something that's not in your book, and I'm just curious about the language and stuff. And what I want to know is how do the summary statistics change? And I'm talking about the mean, standard deviation, minimum, first quartile, median, third quartile, maximum, interquartile range. That's all the stuff we calculated in Chapter 2. Because what's going to happen is we're going to come in and we're going to take our first test. And then when the scores come back, you're going to ask me to curve it. Students always do. It don't matter. Well, you want to be careful in this class asking me to curve because I'm going to ask you what kind of curve you want. What you're going to want to ask is, could you please slide the curve? Because here's the thing. It doesn't matter whether it's a histogram or whatever. Suppose I take all the observations, right? In other words, I take all the test scores and I add 10 to them. Yeah? So let's say I add 10. What does that do to the mean? What does that do to the standard deviation, the minimum, all that? Okay, so what you're doing is you're taking the histogram and you're adding 10 to everybody, so you're picking it up and moving it. Did I do this to it? Did I change anything that measures spread? And the answer is no. So this one gets added 10. That stays the same. That gets added 10, added 10. The spread didn't change. Let's say the test scores are bad. So I come in and we're going to multiply them by 2. Now what did you do? You picked the histogram up and you moved it again, right, by multiplying it by 2. But did you do this? Yeah, you actually multiplied the spread by 2. Everybody gets multiplied. All the summary statistics get multiplied by 2. Now look, if your test scores are really good, I might subtract 10 from everybody's test scores. I moved it to the left, yeah? Did I change the spread? No. Adding or subtracting the same number to all the observations changes location, doesn't change spread. Multiplying or dividing changes location, and it changes spread. Everybody have a good weekend. We'll see you on Tuesday. Don't forget my homework problems for Tuesday.